All right, in this video, I'm going to start talking about some concepts associated with algorithms and asymptotic notation. So notation in data structures, where I'm going to start. I've got some videos in here for you to talk about it, and I'm going to talk about this as well, but this is something that I already had as a resource I wanted to share that is not just applicable to this course, but also in data science course that I teach as well, where we talk about the different sortings and sort algorithms, and then different concepts when it comes to data science, whether it's decision trees, naive Bayes, different types of regression. Okay, so with that said, we're going to focus primarily on notation and the algorithms themselves. Now, let's think about what an algorithm is. And in the past, we'd say an algorithm is like a recipe. Well, yeah, it is. But at this stage of the game, we need to look at an algorithm as more than just the recipe. We want to look at an algorithm from the context of it's the best recipe ever for whatever that may be. I like baking cheesecakes. And yeah, there's a lot of recipes for cheesecakes out there. Some of them, they may take a long time. Some of them may use really expensive ingredients. Some may taste really good. Some may not. And if I want to make the best, it's in certain context. I want it to taste real good and not cost me a lot of money. Not take a long time to prepare and bake. So it's not just a matter of having a recipe. It's at a certain point, we want to make sure that our recipe or our algorithm is the most efficient way to perform that task. Now, this is an example of what's called bubble sorting. And there's more than one way to perform a sort. All right. And we'll talk about those in the next module. But in essence, this is the bubble sort algorithm. This is pseudocode for it. And the things I want to talk about now deal with time complexity and space complexity and the relationship between a algorithm and pseudocode. Now, in the past, you would have the algorithm first and then the pseudocode. Like I said, we're beyond that. Yeah, there's an algorithm to create sorting, but now we're trying to make sure that the algorithm we have for this specific type of sort is efficient. We want to find out how long does it take to sort using this algorithm as opposed to another algorithm, and how do we measure that efficiency? Now, efficiency, we can look at efficiency two ways when it comes to a computer. There's time complexity or time efficiency. How much processing power are we using on that given system to perform this task? If we're talking about a length of an array, length being n, I don't know what it is. I don't know how long it is. So everything we're going to deal with is n, or in this instance, they say length of the array. So I'll say it's n. And in my examples, I prefer to use n. And here we say n. You see the n being used in here. That's how long this thing is, because this is mathematical. Mathematical, we start at 1 and we go to n. I don't need to know what n is. N can be 5. N can be 5 trillion. And I need to look at things from the standpoint that if I'm using an array that is 5 trillion long, then I want to see how efficient this algorithm is at this array that's 5 trillion items in length, as opposed to other types of sort that are 5 trillion in length, and be able to compare. You know, if we're measuring these tiny, tiny little arrays, you know, does it matter how fast it is if it's that fast? It doesn't matter so much because it was so fast I didn't even notice that it ran. In business today, we don't deal with these little things. We don't worry about those little ones. We worry about the algorithms as they apply to massive amounts of data. So if I have an array with 5 trillion pieces of data in it, that's significant. And it will take time if it's an inefficient array. If it's an efficient array, it could be exponentially faster. So how do we measure this time complexity? We'll talk about that in a minute. The other measure of efficiency is space. How much memory, how much space in my RAM, because this thing's running in RAM, how much memory am I using to execute this code? How many variables am I creating along the way that are tying up space in memory? That's a big deal. One, if I don't have enough RAM to do it, this thing will shut my computer down or bring it to a halt, if you will. It won't necessarily shut it down, but it will slow it down to the point that it might as well be shut down because this is going to take forever. So we've got space complexity, we've got time complexity. Now when it comes to time complexity, if I look at this first line right here, for I goes from 1 till the length minus 1. Length is n, and we're only going to go to the last member before I hit the end. So if we're writing a program, this is going to go from 0 to n minus 1. Here we're going to go from 1 to n minus 1. So it's the one right before the last one. 1 right before the last one. And you think, well, wait a minute, why don't I want to check the last one? Well, what we do in here will compare the one before the last to the last. So we're going to take care of that. I don't want to go to the last and then look beyond it. I go to one before the end and look at the end. Now, how many times will I execute that line of code? How many times will I execute that line of code? I go, let's say this is going to go from 1, and the array is of the length 10. So the A stands for the word array. From 1 to 10, well, we're going 1 less than 10. So we're going to go from position 1 to position 9. We're not going to the 10th one. How many times do I go through this line of code? How many times does the computer test to see, are we done? So we come in the first time, and we're at the first item. There's 1. Second item, there's 2. Third item, there's 3. Fourth item, 4. We go all the way up to the 9th item. Okay. And we're at the 9th item, and Have we reached the end yet? Nope. We're at the 9th item, and we execute this code, and we come back up. We don't know that we're done yet. We don't know. We have to do the test and run the test, execute the test, and find out that, yep, we've already exceeded this point and we're done. So are we doing it 9 times? No, we literally do it 10 times. Okay, so the length is n. We're going to execute this line of code n times. So look at the second line. How many times do we execute that line of code? Well, that specific line of code, as it stands, is n times. But wait a minute. If we look at the complexity of the whole thing, we're going to have this n times this n. So that's n squared. How many times do we do this? There's time complexity here. There's time complexity here. Okay. So we're going to get into that when we get into chapter 3. But I just wanted to touch on it that we'll do things n times. How many times is, what's n, what's the value of n? N is however long the array is that we're doing it for. Could be 5 trillion, it could be 5. Does length matter in how long it takes to do things? Absolutely. What we're going to do is we're going to look back here and we're going to look at the notation of data structures. And by default, we call it big O notation. Now, it's more than just big O notation, but the one that we talk about the most is big O notation. Now, big O notation is used to describe the asymptotic upper bound. I'm not going to dig deep into what the word asymptotic means at this point. We'll just look at it as big O notation is us looking for the worst case scenario when it comes to an algorithm. Now, let's say that I have an array and I want to run a sort algorithm on it. If the array is unsorted, how many times will I go through that sort? Well, it'll be n, and we'll talk about that in the next module. Or it'll be n squared. A search will be n. The sort will be n squared. Now, with that said, and I apologize if you can hear the students outside my door. That I have no control over that. But I'll wait till they pass. When it comes to big O notation, we're going to look at worst case scenario. So let's say that we were going to do a search. And on a search algorithm, that's going to be a linear structure. And let me come back to this, what we looked at before. Different types of collections. Here we go. Here's a linear collection. And I want to search for the value that happens to be in D3. How many steps do I have to go through? 1 task, 2 tasks, 3 tasks before I find it. All right. It took me 3 to find it. Best case scenario if I'm searching, and I'm searching from left to right. Best case scenario. It's in the first one, and I found the first comparison. Okay. Worst case scenario. And I don't know how long this array is. And worst case scenario, where is the thing I'm looking for? At the end. How long is it? N. So worst case scenario for this search would be N. Best case would be 1. What's middle of the road? N divided by 2. About halfway. We just average it. So middle of the road would be N divided by 2. Worst case scenario, N. So if I'm looking at the time complexity of a search algorithm on a linear collection, and I go from front to back, linear search, time complexity is N. Now there's other searches that I can do, and what I just looked at wouldn't matter if it was sorted or not. Wouldn't matter if it's sorted or not. I could go look for things in here and do it more efficiently than going one by one. And we'll talk about this later on, but there's a divide and conquer method of finding what the lowest value is. So if I want to find what is the lowest value in this array and it's sorted, well, I can't assume, but if I know it's sorted, I know the first one's it. If it's not sorted, man, that makes it cumbersome, doesn't it? I've got to go through each one. All right. Or I could, if it's sorted, I could do a divide and conquer. Go halfway looking for that search. If it's sorted, it makes it a whole lot more efficient, especially when we're talking about big numbers. 10 trillion, 5 trillion. You can do it a whole lot faster than going linear search. We'll talk about that later. But what algorithmic thinking and what this big O notation allows us to do is to look at things in worst case scenario when it comes to time complexity, best case scenario when it comes to time complexity, and average. Now, we've got theta, which is average, and omega, which is best case. So we've got big O, worst. Theta, which is middle of the road or average. And then we've got beyond that, I think I might have it down at the bottom, or do I? No, I don't. There's no worries. Okay. We'll talk about these more in the next module, but at each level, and a lot of times we'll just default theta up and, yeah, you know what? We'll look at time complexity, even though I got a good idea it's going to be middle of the road. We'll just treat it as worst case scenario because it's safer to figure that, you know what they say, hope for the best, plan for the worst. I hope it's going to be efficient and we're doing things in omega. But you know what? I need to plan for big O, which big O does not stand for omega. So big O is worst case scenario. All right. So when I look at something like this, how many times am I going to go through that statement? N. When I look at this search, and I do a sequential search looking for any of these numbers, if I'm looking for the third number, that's fixed. It's constant. Go find the third number. Every time it's going to take the same amount of time to find the third one. But if I don't know where it is, I got to plan for the worst. And the worst case scenario in time complexity on this linear search is n. Best case scenario is 1. Middle of the road is n divided by 2. There's other ways to go about searches, and we'll talk about those moving forward. Okay. I'll talk about those in Module 3. And I'm probably going to have things, you can go look at that exercise, but I'm probably going to have that exercise that you see in Module 2 do later on. I want you to spend some time playing with it. Okay? So this is the start to algorithms, and we'll carry on from here as we move forward into Module 3.